Okay, so now we're going to look at the ratio test and the root test. I think some of you already know these tests because I saw that you attempted to use these on the previous exam, but you have to be able to use them properly. So let's talk about these tests. All right, so before we do, let's review all of our tests. Okay, so let's review. I like to do this when I do my series. So we're given the summation n equals 1 to infinity of an. And we wish to determine if the summation n equals 1 to infinity of an is less than infinity. In other words, it converges. So let's see here. So the first test we had was the geometric series. Then the second test was the telescoping series. And the third test was the nth term test of divergence. And the fourth test was the integral test. Then the fifth test was the p-series. Then the sixth test was the direct comparison test. Then the seventh test, I feel like I'm missing one. I am missing one, the limit comparison test. No, I'm not. Then the eighth test is the alternating series test. And the ninth test was the test of absolute convergence. And then the 10th test was the test for conditional convergence. And then now we're at the 11th test. It's the ratio test. So that's where we are today. Okay. All right, so we want to let summation an be a series. So we're going to compute the limit as n approaches infinity of the absolute value of an plus 1 over an. That's why it's called ratio, because we're looking at the ratio of these two terms. Okay, and we're going to define this value to be rho. If rho is less than 1, then the series converges absolutely. And you remember, a series that converges absolutely, we say that it converges. If rho is greater than 1, then the series diverges. And if rho is equal to 1, the test is inconclusive. Okay. So the ratio test, whenever you see factorials, those are the best ones to use for the ratio test. So this test, it is very useful. And best suited for factorials. So anytime you have n factorial in your problem, the ratio test is one of the best tests to use. Okay, so here's some examples. So the first test is the summation n equals 1 to infinity of 2 to the n over n factorial. Okay, so this is a perfect one to use. All right. And so when we do this, we now see that an is 2 to the n divided by n factorial. So now we need to find an plus 1. That is 2 to the n plus 1 divided by n plus 1 factorial. Now, if you don't know what the factorials are, let me just briefly stop to say something about it. N factorial is n times n minus 1 times n minus 2, and it goes all the way down to 3 times 2 times 1. Okay, and it is necessarily true that 0 factorial by definition is equal to 1. And n plus 1 factorial means I go out one more number, so I'm going to get n plus 1, but it's still times n minus 1 times n minus 2, and this also goes all the way down to 3 times 2 times 1. So anytime you see these, that's what you're going to use. And notice that in n plus 1 factorial, we have this piece, and that piece is n factorial. So it is necessarily true that n plus 1 factorial just takes n plus 1 and multiplies by n factorial, because I'm just adding one more term. Okay, so this is useful in trying to determine whether this series converges or diverges. The test says compute the limit. We want to see what happens to the ratio of an plus 1 over an, and we will get some number rho. Okay, so let's compute that. So the limit as n approaches infinity of the absolute value of an plus 1 divided by an is the limit as n approaches infinity of the absolute value. Well, an plus 1 is 2 to the n plus 1 over n plus 1 factorial. So this is 2 to the n plus 1 over n plus 1 factorial. So that's a to the n plus 1, and that divides by 2 to the n over n factorial, which is an. So this piece right here is an plus 1, and then that should be in the denominator or in the subscript. And then this piece right here is an. So this now becomes the limit as, and this thing I said is rho. So therefore rho is the limit as n approaches infinity. So now when you divide by a fraction, you multiply it by a reciprocal. So I get the absolute value of 2 to the n plus 1 divided by n plus 1 factorial times n factorial divided by 2 to the n. Okay, so this is always really a very nice problem when you're looking at factorials, because now I have the absolute value of 2 to the n plus 1 over 2 to the n, and then n factorial over n plus 1 factorial. Okay, I forgot my limit. Okay, so therefore rho is equal to, now when first of all, I don't need absolute values anymore, everything's positive. 2 to the n plus 1 over 2 to the n is just 2. And then n factorial over n plus 1 factorial, if you remember, we said n plus 1 factorial is just n plus 1 times n factorial. So this is 2 times n factorial over n plus 1 times n factorial. Okay, again, I forgot my limit. Times n factorial. So now you can easily see the n factorials go. So this is the limit as n approaches infinity of 2 over n plus 1, and that limit is 0. Aha! 0 is less than 1. So we have rho is less than 1. So that implies this series converges. Now, what it converges to, we don't know, but we do know it converges. Okay. Let's look at number 2. Again, if you have, yes?
I was going to say, Destiny put a question in the chat.
Okay, thank you. Could you explain why it's just 2? Okay, thank you. Good question. All right, Destiny. Excellent question. Okay, so on the side, we have 2 to the n plus 1 divided by 2 to the n. So when this is the same as 2 to the n times 2 to the 1 over 2 to the n. Because when you multiply, you add exponents. So you multiply two elements that have the same base, you add the exponents. So therefore, 2 to the n plus 1 is just 2 to the n times 2 to the first power. So therefore, I can conveniently divide out the 2 to the n's and just get 2. Excellent
Okay,
question.
thank you.
Yep, you are not the only person who was probably wondering that. Excellent question. Okay. Any other questions? You guys are a great class. I'm going to miss y'all. Okay, so we have the sum n equals 1 to infinity of -1 to the n over n plus 2 divided by 3 to the n. Okay, so there's several things I can do with this problem, okay? I could use the test of absolute convergence, so we could do that. And if we use that test, we would have to show the summation n equals 1 to infinity of n plus 2 over 3 to the n converges. And if that converges, then we know the original series converges. But we're going to use the ratio test. Okay, so an is -1 to the n times n plus 2 divided by 3 to the n. And an plus 1 is -1 to the n plus 1 times n plus 1 plus 2 divided by 3 to the n plus 1. Okay, so if you notice, everywhere there was an n, I just put n plus 1. So now rho is the limit as n approaches infinity of the absolute value of an plus 1 divided by an. So now, since I know I'm going into absolute value, I'm not going to need the negative ones. They are going to be gone. But I'm going to have an plus 1 divided by an. So that's going to be the limit. N approaches infinity. The absolute value, I'm going to have n plus 3 over 3 to the n. And when I divide by an, I'm going to get 3 to the n over n plus 2. Okay. So this is now the limit as n approaches infinity. So I'm going to make this, everything's positive, so I'm going to drop the absolute value. Okay. So now I'm going to get n plus 3 over n plus 2. And then I'm going to get 3 to the n over, whoops. This one should have an n plus 1 over 3 to the n plus 1. Okay, so this is what I'm taking the limit of now. So now this is the limit as n approaches infinity. I'm going to get n plus 1, nope, n plus 2 over n plus 3. And then again, destiny, this is the same type of problem. 3 to the n is going to cancel with the 3 to the n, but leave a 3 in the denominator. And so when I take the limit, n plus 2 over n plus 3, the limit of that is just 1 times 1/3. That's equal to 1/3, which is less than 1. So therefore, this series converges. Absolutely. This one should say absolutely as well. Okay. Okay, here's another one. I don't know what number that was. Was that 2? Okay.
Shouldn't,
Number 3. Yes. That
shouldn't
is,
that n+3 be on top? Or
let me see. n+3 should be on the top. Okay, so that's 2 mistakes. First off, this one should be an n+3. And then over here, this on the top should be n+3, and this should be n+2. And the limit of that is 1. Okay. I think I fixed it now. Thank you. Okay. Number 3, the limit as n approaches infinity, the log of n over n factorial. Okay, so an is equal to the log of n over n factorial, and an plus 1 is equal to the log of n plus 1 divided, whoa. Divided by n plus 1 factorial. So rho, the limit as n approaches infinity of the absolute value of an plus 1 over an, and that's the limit as n approaches infinity. Don't need absolute values because everything is positive. So I'm going to end up with the log of n plus 1 divided by n plus 1 factorial. And that's going to be times n factorial divided by the log of n. Okay. So now this says rho is equal to the limit as n approaches infinity. So now how do I deal with this? Let's put the log of n plus 1 over the log of n. And let's put n factorial over n plus 1 factorial. So now I get, this is the limit as n approaches infinity. Now, how do you evaluate this limit? How do you evaluate that limit? Okay. And this is going to give me 1 over n plus 1. So I need to figure out what this is doing. I know 1 over n is going to infinity, so I need to figure out what this is doing. Okay, so let's figure that out for a moment. the limit as n approaches infinity of the log of n plus 1 divided by the log of n. Let's use L'Hopital's rule. So the derivative of the top is going to be 1 over n plus 1. Whoa, forgot my limit. So the derivative of the top is 1 over n plus 1. And the derivative of the bottom is 1 over n. So this is the limit as n approaches infinity of n over n plus 1. And that's just 1. You can use L'Hopital's rule again and get 1. Okay, so therefore rho turns out to equal 1 times 0, which is 0, which is less than 1. So this series converges absolutely. Okay, number 4, summation n equals 1 to infinity of n plus 3 over n plus 2. All right, so if I'm not smart enough to figure out to use the nth term test of divergence, which is what I should use here, if I try the ratio test, I'm going to get rho is equal to 1. And so the ratio test will be inconclusive. So I don't want you to be gung-ho to rush and rule the ratio or root test, because sometimes there's another test that will give you the answer right away. Okay, so I have a whole bunch of problems we can solve, but we're going to do, the next one is going to be the root test. Okay. I love the ratio and the root test, but the root test, man, this test is quick and dirty. It does its job. It comes in, swoops in, does its job, and leaves. That's the ratio, the root test. Okay, so again, let summation n equals 1 to infinity of an be a series. So now again, we're going to compute rho, but this time rho is the limit as n approaches infinity of the square root of the absolute value of an. So we're going to compute that. If rho is less than 1, then the series converges. If rho is greater than 1, then the series diverges. And if rho is equal to 1, the test is inconclusive. Now, the reason why I like this test is because, like I said, this test is quick and dirty. It's quick. But this test makes use of one major limit. And that is a lot of times you will use the fact that the limit as n approaches infinity of the nth root of n is 1. If you use that, you're in good shape. So we'll find a couple of places where we're going to need that. Okay. And I think there was another one that was also important. Let me find that one. Okay. And the second thing is that the limit as n approaches infinity of the nth root of any number x is equal to 1 as long as x is greater than 0. So the nth root of any number is equal to 1. Okay. All righty.
Dr. Lott,
Yes.
you have 2p is less than 1.
Ah, thank you. All right. P is, and that's rho actually, but that's good. I'm fine with that. If it's greater than 1, then it diverges. Okay. All right. So let's look at this. So number 1, so here's some examples. The first one is easy, 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 quick and dirty. Summation n equal 1 to infinity of 1 over 2n plus 7 to the nth power. Now remember, when something is raised, when you take the nth root, if you remember the nth root of anything is simply that thing to the 1 over n. So that's basically what that means. Okay, so here, identify an. It is 1 over 2n plus 7 to the nth power. So therefore, rho is the limit as n approaches infinity of the nth root of the absolute value of an. So that is the limit as n approaches infinity of the nth root of 1 over 2n plus 7 to the n. Y'all should be able to see this already. So this is the limit as n approaches infinity. I'm going to drag it out. This is 1 over 2n plus 7 to the n raised to the 1 over n power, which is the limit as n approaches infinity of 1 over 2n plus 1. Okay. All righty. And again, as we said, the nth root of any number greater than 0. So actually, if I really want to be specific, I need to make this 1 to the 1 over n power. All right, so this goes to 1. Oh, so the whole thing goes to 0. Actually, the nth root of that 1. Yeah, that goes to 1 and n goes to infinity. So this thing, whole thing goes to 0. Okay. number 2, summation n equals 1 to infinity of e to the minus n times n cubed. Now, this one, I could use the integral test. Okay, we could. It's a lot of work. That looks to me like integration by parts 3 times. So yeah, that's a bit of work. And since I don't want to spend that much time doing it, I'm going to use the ratio test. I'm sorry, the root test. Actually, you can use the ratio test on this one as well. Okay. So I could use the root test, the ratio test, and the integral test. So we're going to use the root test. So we're going to let an is e to the minus n times n cubed. So this time, let's compute. An is positive. So let's compute the absolute value of an to the 1 over n power. So that's going to give me e to the minus n cubed to the 1 over n. So therefore I get the absolute value of an to the 1 over n. Well, I get e to the minus n times 1 over n becomes e to the minus 1. And then I'm going to get n cubed to the 1 over n, but that's the same as e to the minus 1 of n to the 1 over n cubed. Aha, now we're ready. So rho is the limit as n approaches infinity of the square root, the nth root of the absolute value of an, but that's just the limit as n approaches infinity of e to the minus 1, n to the 1 over n cubed. So that goes to e to the minus 1. This goes to 1 cubed. So I get 1 over e, which is less than 1, so it converges. Absolutely. Okay. What did I write here? Again, this series converges absolutely. Okay. All right, so let's look at this. Number 3, summation n equals 1 to infinity of 4n plus 3 divided by 3n minus 5, all raised to the nth power. Okay, so therefore an is 4n plus 1 divided by 3n minus 5. All right, raised to the nth power. So this one I am going to need the absolute value. Okay, although we can assume as for n bigger than for n bigger than 2, an is positive. All right. So therefore, we're going to have the nth root of 4n plus 1 divided by 3n minus 5. That should be to the n. and that should be an absolute value. So that looks like 4n plus 1 over 3n minus 5 to the nth power, and then it gets raised to the 1 over n, because that's the nth root. But that just becomes the absolute value of 4n plus 1 divided by 3n minus 5. Okay. So now rho, which is the limit as n approaches infinity of the nth root of absolute value of an, just becomes the limit as n approaches infinity of the absolute value of 4n plus 1 divided by 3n minus 5. And that limit is 4/3. That's greater than 1, so this series diverges. Okay, any questions? All right. Sum n equals 1 to infinity of minus 1 to the n divided by n to the 1 plus n. Oh, this is beautiful. Beautiful, beautiful problem. Okay. So I'm going to use the root test on this as well. All right, so an is minus 1 to the n over n to the 1 plus n. So the absolute value of an is just 1 over n to the 1 plus n. So the absolute value of an to the 1 over n power is just 1 to the 1 over n divided by n to the 1 plus n to the 1 over n. All right, so what happens to that? So this looks like I get 1 to the 1 over n. I know that's going to go to 0. But now I get n to the 1 over n times n to the first power. Because now I have to distribute this power. So I have to distribute this. When it multiplies by 1 over n, then it multiplies by n. So I get n to the 1 over n and then n. Okay, I think I'm ready. So rho is the limit as n approaches infinity of the nth root of the absolute value of an. That's the same as the limit as n approaches infinity of the absolute value of an to the 1 over n power. So that's the limit as n approaches infinity of 1 to the 1 over n divided by n to the 1 over n times n. So 1 to the 1 over n goes to 1. Up. Yeah. N to the 1 over n goes to 1, and n goes to infinity. So this limit is 0, which is less than n, so it converges. Okay. Here's a hard one that's actually easy. Sum n equals 1 to infinity of the sine to the n of 1 over the square root of n. Okay, again, root test. So an is the sine to the nth power of 1 over the square root of n. So therefore, and it's positive, so we're going to take, well, it's not positive. We have to take the absolute value of an, the absolute value of the sine of 1 over the square root of n to the nth power. So therefore, the absolute value of an to the 1 over n is the absolute value of, well, I don't need to write it again, is the absolute value of the sine of 1 over the square root of n to the nth power to the 1 over n. So the 1 over n's cancel. So that just gives me the sine of 1 over the square root of n. So now rho is the limit as n approaches infinity of the absolute value of an to the 1 over n power. So that's just the limit as n approaches infinity of the sine of 1 over the square root of n. As n goes to infinity, 1 over the square root n goes to 0. The sine of 0 is 0. Okay, I'll actually write that out. Okay, any questions about that? I have several more examples, but I want to look at something. I was working on your exam, and I just realized I may want to show you the first part of it, just so you know. So let me do this. Aha, okay, this is the first page of your exam. Okay, so let me new share that. Okay, so this is what your exam looks like. All right, just want to be clear. I hope you should be able to see it. The first thing, as always, you must show all work to receive credit. No work, no credit. If you just have converged, I'm not giving you credit for that. Determine if the series converge or diverge. All of these series can be shown to converge or diverge. If the test is inconclusive, you can't just say this test is inconclusive. You have to use another test because these series that I'm giving you converge and diverge. You will get 2 points earned for stating that the test you use to determine your conclusion. So you get 2 points for saying the ratio test, the root test, the integral test, the telescoping series test, the p-series test, the nth test of divergence, the direct comparison, the limit comparison, ratio, root, alternating series, tests for absolute convergence, and tests for conditional convergence. So you will get 2 points, okay, out of 10 for writing the name of the test. So don't forget to write the name of the test that you use. 5 points for justification. So all that work that we just did, showing that rho is equal to the limit of whatever, all of that is the justification, showing why your test gives you the correct use of the test. 2 points for showing how the test helps you arrive at your results. That means if the test you get to rho is equal to 0.5, then you say is less than 1, it converges, then you will get 2 points for being able to show that you use the fact that rho was less than 1, and then you will get 1 point for saying that your final answer is to converge. If you do a test and you get to something, let's see, alternating series test, and you satisfy parts 1, 2, and 3, and you show that the limit of the UN goes to 0, and so all 3 conditions, if you have all 3 of those, that will count for 5 points. That is your justification, okay, of the use of the test. Now, there are going to be problems on the test that are worth 15 points. I'm not going to tell you which ones, because you will have to figure that out. They are the ones that are alternating series, geometric, and telescoping series. These series on the test will count for 15 points. Okay, so you will get 5 additional points if it's an alternating series test, and you go on to show that it is absolutely or conditionally convergent. Okay, if you do an alternating series test and you conclude that your series converges, you then must go further. This is not extra credit. You must then go further to say whether it converges absolutely or conditionally. If it is a geometric series test, and you write that I am using the geometric series, and then you say the absolute value of R is less than 1, so therefore I show that, and therefore I can say that my test is convergent, so you will get all 10 points, but then you must continue on to get the additional 5 points for a geometric series test. You have to compute the sum. Otherwise, you will only get 10 out of 15 points for any problem that is a geometric series. And any problem that is a telescoping series, you will get 10 points for taking your telescoping series, computing your nth partial sum, showing that is equal to some number, and then concluding that it converges. And for that telescoping series, provided you compute the sum correctly, you will get 5 additional points. Okay, any questions about how you are going to be tested on these series? Any questions?
Are there any extra credit questions?
There will be 2 extra credit series problems on the test.
Thanks.
There will be 2.
Oh, I do have a question. I just want to ask, I know we have 8 tests. So I was going to say, like, is it 8 including the final exam, or is it like 8
No,
and
test
then
8
the
is by
final?
itself. Test 8 is by itself, and then the final.
Okay, thanks.
Okay. Any other questions? Okay, just looking at the chat. All right, so this is my multiple choice series. I think there is only one student in this class who I have actually had before for Calculus 2. I think for everybody else, this will be new. And so what you are to do, we're going to work on the first 3 problems. Let's just do the first 3. And so with the first 3, you are to state which test you can actually use for this particular series. So for the series n equals 0, minus 1 to n, and 4 over 5 to the n, there are several different tests that I can use for this series. So I would like somebody to volunteer to see if they could give me the number 1. And if you don't pick them all, that is okay. Somebody else can pick some too. So don't feel like you have to pick them all. Just if you at least pick one test, I'm happy for you to volunteer.
I could go. Well, I
Okay,
know. I think I know two.
okay,
Geometric and alternate series test.
okay. So we have the geometric series test and the alternating series test. So now with the alternating series test, what would you have to show?
You would have to show that U of n is, I think, greater than 0.
Yes.
Yeah, greater than 0. And then the derivative of U of n is less than 1, I believe. Or is it less than 0?
Well, for this one, you could do that. This one is actually easier to show that un plus 1 is less than un, because you're basically showing that if you raise 4/5 to a bigger power, it's going to get smaller. So that one's pretty, but you
Oh,
don't
yeah.
have to take the derivative in this one. This
Oh.
one is easy. Okay, but yes, the alternating series test will work. There is one other test that will also work. Actually, there are two other tests that will actually work. So the two tests we just did today. All right, the root test will definitely work because you're going to get rid of that nth power. So when we see the nth power, oh yeah, we definitely want to use the root test because we're going to take the absolute value. Okay, so that will work. And also the ratio test will work. Okay. All right. Any questions? All right, how about number 2? I forgot these don't have numbers on them. They're supposed to. There really is only one test that you can use on this one. Anybody have an idea?
I think P series. I'm not sure. I'll say P series, but I'm not sure. No, not P series. Nth term test.
Okay, so possibly the nth term. Actually, okay, so you're right. There are actually more than one test. There's 2 tests. I forgot about that one. You could use the nth term test of divergence. It will not fail in this case. For this one, it actually will work. You will show that the an actually goes to infinity. But another test you can use is the ratio test. If anybody wants to see any of these, please say so, and I will go through the problem for you.
I'd like to see it.
Okay.
For
I'm
ratio.
about to take your offering. I'll take it.
That's all right. Oh, hey, you have not because you ask not. Okay, so which one you wanted? The second one? Summation n factorial over 10 to the n. Okay. Is it 1,000 to the n? Okay. All right, so this one, again, as I said to you before, factorials are always wonderful for the ratio test. Okay. Now, if I wanted to try to just use the nth term test of divergence, okay, so an is n factorial over 1,000 to the n. But after the 1,000th term, so up until we get to the 1,000th term, the biggest numbers in the numerator are anything from 1,999. So let's look at the A1000th term. It's 1,000 times 999. And then underneath it, this goes all the way down to 3 times 2 times 1. And underneath it, I'm going to have 1,000 times 1,000. And it's going to go like this, times 1,000, 1,000, etc. But after the A1000th term, the numbers that start getting multiplied are humongous. So let's say if we look at the A1005th term, we're now going to have 1,005, 1,004. So these numbers get bigger up here, whereas the bottom numbers still stay 1,000. These still stay 1,000. Nothing you can do, they're always 1,000. So when you're looking at A1 millionth term, again, now you got numbers that are in the millions in the numerator and numbers in the denominator that still stay 1,000. So this actual number goes to infinity. So by the nth term test of divergence, this thing diverges. Okay, but if we use the ratio test, we're going to let
Why-
AN question.
Yeah, I was gonna say, why does it always stay 1,000 on the bottom?
Because the bottom is 1,000 to the n. So if I had the 1 millionth term, A1001, let's say 100,000. In the numerator, I have numbers like 100,000, 999,999. I have these big numbers, but in the denominator, I will have 100,000, 100s, 1,000s. I'm still going to get now 1,000 multiplied by itself 100,000 times, but the numbers in the numerator are way bigger.
Oh, I see now. I see.
Okay.
Thank
Okay.
you.
They just keep getting bigger and bigger. Okay. All right, so let's look at the ratio test. So AN is n factorial over 100 over 1,000 to the n. And AN plus 1 is n plus 1 factorial over 1,000 to the n plus 1. So rho equal to the limit as n approaches infinity of the absolute value of AN plus 1 over AN is the limit as n approaches infinity. And then I'm going to get, well, these are all positive, so I can drop the absolute value. So I'm going to get 1,000 to the n plus 1 over n plus 1 factorial. That is wrong. I'm getting AN, which is n plus 1 over 1,000 to the n. Okay. I may not be here when you get back. I gotta step out. 1,000 to the n over n factorial. Okay. So this is the limit as n approaches infinity. The n factorial over n factorial, that's just going to give me n plus 1. The n plus 1 factorial over n plus factorial, it's going to give me n plus 1. And then I'm going to get 1,000 in the denominator because 1,000 to the n is going to kill off that and leave this 1,000 to the first power. And so I can easily see this limit is infinity, which is much greater than 1. So the series diverges. Any questions?
I had a question.
Okay.
So the way that we get to the a n plus 1 over a of n, or a n, is
Yes.
that we take n and we replace it with n plus 1 to do the whole ratio.
So, okay, so first, if you notice, I have the ratio test is, I need to compute rho is the limit as n approaches infinity of the absolute value of a n plus 1 over a n. So I always compute a n first. I find a n. So first thing is I pull out whatever a n is. Then I find a n plus 1. So I find a n, and then I find a n plus 1. And then I usually compute what the ratio is. So as you can see, whenever it's a fraction, you always end up multiplying by the reciprocal of an. But yes, you have to use n plus 1. The n plus 1 comes from this term right here. So this first thing, this is an plus 1. That is an plus 1. And then I divide it by an. So this is division by an. Okay, any questions? Okay. All right, the third one. Summation, n equals 0 to infinity of 5 over n cubed plus 15. There are 2 tests I can use for this. One is easier than the other. Hello? Any hint on this one? Okay, I'll give you a hint. As n gets really big, and this is the way you got to think with these kinds of problems sometimes. If n gets really big, am I worried about that little 15? And if I'm
No.
not, what does this series look like?
Can it
So,
be n term?
what's that?
Can it be like nth term?
So this looks like n equals 0 to infinity of 5 over n cubed plus 15. Now, as n gets really, really big, n cubed plus 15 kind of looks like just n cubed. So therefore, this series, the summation n equals 0 to infinity of 5 over n cubed starts to look like the summation n equals 0 to infinity. This is n cubed plus 15. Starts to look like 5 over n cubed. Now that I know what it starts to look like, now I need to focus on this. So once I start focusing on that, I now know that I can compare, woo, that's a big word right there. I can compare the two series. So I could either use the direct comparison test, where I look at an is 5 over n cubed plus 15, and bn is 5 over n cubed. And an is less than or equal to bn always, because n cubed plus 15 is always bigger than n cubed. And the summation n equals 0 to infinity, actually n equals 1 to infinity of 5 over n cubed is equal to 5 times the summation n equals 1 to infinity of 1 over n cubed. What do you know about this series? What does that series do?
It approaches 0.
No, not quite. I want to know whether or not it converges or diverges. So I got to use one of my 10 tests.
Because of P series, since P is 3, it converges.
Okay, so this series is a P series where P is equal to 3. And so this converges. So that altogether implies that the summation n equals 0 to infinity, 1 over n cubed plus 15 also converges. So I will post that sheet. I'll either post it or send it to you by email so you can look at it and work on it over the weekend. I'll post this video as well. And then you guys will have a couple of things to work with. To look at.